So today in the seminar of GERAD, we have Martin Schmidt, full professor at Trier University in Germany. He's also vice speaker for the research training group Algorithm Optimization at Trier University. He's also fellow of the Energy Campus Nuremberg, deputy professorship in nonlinear optimization, which is, I think, his expertise. Martin also serves as associate editor of OR Spectrum, for the Euro Journal on Computational Optimization, and he is also technical editor of the Mathematical Programming Computation. It's a pleasure for me to have him here, speaking about a problem that has a long relation with the GERAD, which is the minimum sum of squares problem. It's a problem that several researchers here in the center are interested about. So thanks, Martin, for your availability in coming here today. And you have the word now.
Okay, thank you very much. Thanks for the nice introduction and for the invitation and the possibility to let me talk a bit about this problem. And I know that I'm talking digitally in front of experts on this problem. And I have to say it's still work in progress. So we are not yet fully done with writing down the preprint. So whenever you have any comments, whenever you have any feedback, just let me know. You can interrupt me also whenever you want during the talk. So just open the microphone and ask. Okay, so let's start. So the first disclaimer that I have to give is that I did not really do all the work that I'm going to present here. So the 4 people that you see here are the ones who worked much harder on these things, especially Karina, who is also here in the audience. And so let me check. So this is the outlook of my talk. So in the beginning, I will give you a brief motivation and introduction into the topic itself. I think most of you know the problem, but maybe some do not. So I will try to wrap up a bit what it's all about. And then in the very short second section, I will talk about 2 possible MINLP formulations for this clustering problem, the minimum sum of squares problem. And what we then do is we try to solve this problem to global optimality. And we use for this mixed integer nonlinear optimization solver. We use, to be specific, SCIP, which is an open source framework for solving mixed integer linear and also nonlinear optimization problems. And it's nice that it's open source because it allows you to, extend it by your problem-specific techniques. And the techniques in particular that we investigated for enhancing the solution process for the MSSC problem are cutting planes, propagation techniques, branching rules, and primal heuristics. I guess it will take me 1 second also talk about symmetry breaking techniques, but they do not deserve a special, say, subsection here because this is all just built in the solver that we use. And in the end, I will, of course, talk a bit about the numerical results and the progress that we made in order to solve the problem to global optimality. Okay, so let's start with the motivation and the introduction. So what is the MSSC problem, the minimum sum of squares problem? So the data that we are given is that we have n data points in some RD, so in some dimension, D. And I will always call, by the way, you see my mouse pointer as well, right? So I can use it as a pointer, right? Good. So I will call these points always small p, and the set of all points that we are given is capital P. So this is a subset in RD, and we have n of them. So the cardinality of capital P is small n. And then we are given a number of k clusters. So k shouldn't be 1 because then it's a trivial problem. And also, if it's n, it's a trivial problem, by the way. So it should be usually something in between. And in the numerical results later on, I will completely focus on the case of k equals 2, but we will also have in the paper later on some more results for larger k. And the task that we have to face in this MSSC problem is to find an assignment of every data point to exactly one cluster. So we want to say, well, data point 17, you belong to cluster 5, for instance. And we do this for every point. And in the end, we want to find one representative point for every cluster. And here for the minimum sum of squares problem that we are solving, we just take the barycenter of the points that we assign to a cluster. So we do not assume that this point really belongs to the data set. It can be any point which is also not in the data set that we are given. And this is a key problem in unsupervised machine learning. So it's unsupervised, of course, because we have no labels given. Okay, we do not know at the beginning to which cluster which point belongs. So this is why it's unsupervised. Okay. So let's put it a bit more formal. Let's call these centroids. These are the representatives in the end that I just talked about. Let's call them Cj, where J is the index of the k clusters that we are going to consider. And the problem in a very abstract way reads that we then have some loss function. I will make this more specific in a second. It depends on the data set of points that we are given, and it depends, of course, on the centroids that we have to determine. So this is in a very abstract way of seeing the problem, our variable, and we want to minimize this loss function. And this loss function, for instance, could be given as follows. So you sum up here first over all the clusters, and then you sum up over all the points, P, that you put into cluster J. Let's call this set Sj. So Sj contains all the points that you assign to cluster J. And then you take, well, the minimum of the sum of squares. And this is what you see here. So you take the distance between the point P and the centroid J, and you square this distance, this 2 norm here. And of course, this formulation is not, well, it's cheating, right? Because the problem is, upfront, you do not know what Sj is. I mean, if you would know what the correct assignment of points to clusters is, then the problem is, of course, trivial. But if you know it, you can write it down as such, just to give you an idea at the very beginning. And I mean, it's easy to explain in the picture, right? So if you take a look, for instance, on the left-hand side, you see here these data points. They are plotted in blue. So this is a 2-dimensional problem. And you very clearly see that you have 8 clusters here. And on the left-hand side, you also see some maybe globally optimal solution of this problem, which are the representative, the centroids, which are the black crosses. But on the right-hand side, you also see that since this is a global optimization problem, a non-convex mixed integer nonlinear optimization problem, I will write this down a bit more in detail later on. You can get locally optimal solutions or feasible solutions that are very bad. And visually inspecting this, it's trivial to see, right? So of course, it's a stupid idea to make 2 clusters with 2 representatives here and only 1 here. And we will come back to this example later on. Okay, but given these blue points, the question is, which blue points do you assign to which cluster? And for every cluster, you have to find a representative. That's the problem. So there are very many areas of applications. So usually in these unsupervised machine learning tasks, you, for instance, have these vectors P that are given, such as the collection of some features of a measurement. So think about gender, age, income, health status, vaccinated once, twice, whatever you might think of, okay? And well, the areas of applications are uncountable, I would say. Here are just 5 of them with some primers to the literature here in data analysis, market segmentation, but also in economics and, for instance, in social science. This is used a lot. Okay, I'm not going into the details here for the applications, but just to let you know There is a lot. Okay, is it a hard problem? Yes, it is. So even if you only consider it in 2 dimensions, it's an NP-hard problem. And there are more papers on this result, or it's proven in more than 1 paper. But for instance, Daniel also in his 2009 paper considered the hardness of this problem. And there are also other papers that state this. And we will see later on in the first numerical results that I will present to you that if you just take an out-of-the-box, state-of-the-art MINLP solver, and yet you just apply it to these problems, you have no chance, okay? Still today. So what are people doing in the applications? Well, usually they use heuristics. In fact, the bad solution that I showed you on the slide before was a heuristic solution found by mainly, I guess, the most important or most prominent heuristic for this problem, which is the k-means clustering problem, which goes back, I guess, to McQueen in the 60s. And it was also later on discussed in very many other papers, for instance, here in this important Lloyd paper in 82. I will come back to this k-means clustering algorithm later on as well, because we will use it as a primal heuristic in our global solution approach as well, because it's just easy to implement and to use. Okay, so a few months ago, Daniel also gave a talk on a similar topic. And there was one particular slide that I liked a lot, and this is why I'm stealing it here. I hope this is okay. At least it's properly cited. And what he talked about was that, well, since this is an unsupervised machine learning task, it is really essential for applications to get global optimal solutions. And the reasons that he gave, and I'm just copying it here, is that since you do not have these labels in advance because it's an unsupervised task, every clustering that you compute needs to be interpreted kind of afterwards by an expert from the domain of the application. And if you give a bad clustering result, the interpretation, even if it's an expert, might be completely strange and crazy, okay? So the only thing to avoid this is to get global optimal solutions, because then you do not have to have these doubts. You simply know, well, that's it, okay? So this is the first and last slide that I stole for this talk today. But what Daniel was talking about was, in his specific application that he published in 2020 with some co-authors, a convex variant of these clustering problems, or of this clustering problem. So the MSSC problem is not the only clustering problem that you can think of. There is an entire zoo of clustering problems that you could find in the literature. And there are also convex ones. And if you have a convex optimization problem, then global optimality, of course, is not an issue usually, because you know that all local optima are also global optima. But the problem that we are considering here is not convex. So we have to face this global optimization task, kind of. And that's the main motivation for what I'm going to present in the following. And here again is the picture that tells you that if you have a suboptimal that is not globally optimal solution, what you see, for instance, here on the right, which is a solution of this famous McQueen algorithm, the k-means clustering algorithm, well, of course, this leads to bad interpretations later on if this is about cancer treatment or whatever. Yeah, you don't want to have this in your discussion about such severe aspects of life. Okay, so just if you are bored and if you need some reading advice for the weekend, here is a brief history of the literature on how to solve this problem to global optimality. So I'm not going to discuss all the papers here, of course, in detail, but just to give you some main papers. So as far as I know, the first branch and bound method for the clustering problem is Fukunaga and co-authors from 75. And it has been reconsidered and refined by Deere in the 80s. And still in 2006, there are papers that are mainly based on these branch and bound methods. They have been combined, for instance, with these famous relaxation linearization techniques by Shirali and Desai. And there is a follow-up paper by Daniel and Hansen, who showed that maybe RLT has to be considered with a bit, one has to be careful with the numerical results that have been reported. So RLT was maybe not the best idea. There are symmetry breaking techniques in the literature. And I guess one of the most best performing ideas is column generation. I'm not going to talk about column generation, but you should at least know after this talk that column generation is a very important algorithmic technique for solving these problems. For instance, again, Daniel worked on these problems. There's something about Benders decomposition. You have conic reformulation. Some people use geometric concepts like Voronoi diagrams. And also in the last, say, 20 years, there are quite some papers that also use semi-definite programming techniques to solve the problem. And finally, there are also, in the last year, they are published some, which we wrap up here with reduced space techniques. And I will come back to this later on as well. Okay, so how do you write this down as an MINLP? That's super easy. So you just introduce a binary variable for every point and cluster. It's 1 if you assign the point to the cluster. It's 0 if not. Then you can reformulate this H function without cheating. And you get rid of the cheating by just multiplying your norm here with the variable that decides on whether your point belongs to the cluster or not. Okay, so there is a 0 if not, and otherwise you count the distance. And of course, every point should belong to exactly one cluster. So you also have this SOS1 type constraint in your model. And then that's it. The objective function I showed to you, you have this SOS1 constraint, you have binary variables, and you can also claim that the centroid variables, Cj here, belong to some bounded set that you can compute in advance. You can, for instance, just take the bounding box of all the data points, and then you have at least bounded continuous variables, which is in global optimization usually something that you like to have. You don't need these bounds for the correctness of the formulation, but usually it helps for solving the problem. But that's trivial, okay? So you only have linear or mixed integer linear constraints, but you have a non-convex cubic objective function, right? I mean, the Cj norm square terms here are quadratic, and then you multiply them again with a variable. So you have, at a first glance, a cubic objective function. So here's another one that we use, which is the so-called epigraph reformulation. And what you do is you just take for every point P and for every cluster J, a new variable eta Pj, so that eta Pj has as its value the distance between P and Cj if P is assigned to J and 0 not. So why is this the case? If it's assigned as such, then this variable is 1, this is all 0, so eta should be larger than this distance. You minimize it, so you get an equality in the optimal solution. If this is 0, then you have this big M here that you subtract. So you minimize, and since you say, well, these distances should all be non-negative, they get 0. So this is very easy to understand. Everything else is exactly the same. So this is, from an MINLP point of view, maybe a nicer formulation because the objective function now is linear and you have only quadratic constraints instead of a cubic objective function. And this quadratic constraint is a convex one because you only have this norm here on the left-hand side, and norms are convex functions. Okay, so we will use both of these formulations later on. So let's start with the discussion of the mixed integer programming techniques that we now invented, or that we use at least in order to solve the problem to global optimality. So let's first talk about cuts. And of course, we also tried to, it was only one thing that we stole from the literature. We steal one more thing, and these are these cardinality cuts, but it's again properly cited here. So that this is not our idea. It's a simple idea. You know that in an optimal solution, there cannot be a cluster that is empty. This is a direct contradiction to optimality in the end. So the sum of all these xpj, if you sum over all points, needs to be larger than 1. And if you apply exactly the same argument, then you also get an upper bound, which is the one that you see here. So that's easy, of course, but you get a first feeling on how to derive maybe cutting planes for this problem. And maybe one more word regarding the importance of cutting planes. I mean, if you have a global optimal, a global solver, as you know, it's all about primal and dual bounds. And if they meet, you have solved the problem. The MSSC problem is a bit special here. Why is it special? Because the primal world usually is never a problem. Almost everything is feasible. Just give every cluster 1 point and then sort everything randomly to clusters. This is a feasible solution. It will have a very bad objective function, but feasibility almost never is a problem. So your primal bound usually is not the problem. But proving optimality, that is getting a good dual bound, is the crucial thing. And what do you do in order to improve your dual bound? You usually think about valid inequalities, cutting planes, etc. Okay, so this is why these valid inequalities are very important. And this is why we thought at a first glance, well, we could localize these cuts. I mean, these cuts you can write down in every node of the entire branch and bound tree. But if you're down the tree somewhere, you have some more information. So you could tighten these cuts. I don't explain this in detail. It's rather easy to do to get localized valid inequalities. That is, valid inequalities that are only valid for the subtree defined by a certain node in the branch and bound tree. Well, it didn't help much. So this is why I'm not going into the details here. You don't try it, okay? We tried it. It will not be a game changer. But we had another idea that is a bit smarter than localizing these cuts that already exist in the literature. And this is using the convex MINLP that we get by the epigraph formulation and just use outer approximation techniques. So if you have a convex feasible set, you know that your first order Taylor approximation at every point gives you a global underestimator of your convex function. So just taking Taylor first order, you get a valid inequality. So you take this convex constraint, it's the epigraph reformulation constraint. You do Taylor first order, et voila. And then you can have an outer approximation scheme embedded in your branch and bound scheme that you use anyway. So whenever you approach a, say, binary feasible point, you can just plug it in and get such a cut. And by this, you improve your dual bound usually. We will later come back to this in the numerical results and check whether it really helps. Okay, so it's just using 1986 idea by Duran and Grossman. It was refined by Fletcher and Leifer and by Grossman and another co-author, Kuseda, later on as well. But yeah, it's just a standard outer approximation cut for the epigraph reformulation. Okay, let's talk about propagation techniques as a second type of mixed integer programming technique that we used. So instead of propagation technique, you can also think about node pre-processing. So think about your branch and bound tree, and you're now at one specific node down in the tree. So you have some additional branching information and some further reductions that the solver just did based on the branching that was already done. Then you can usually use these further reductions on your own to derive further variable fixings or further reductions of variable bounds, etc. And you can do this usually a bit better than the solver because you know the problem. You know the geometric properties. You know that it's not just a generic MINLP, but that there is some picture behind. But there's one challenge. If you take a look in the MINLP literature, usually, and that's usually the easier way, at least for my personal way of thinking, is to derive these propagation techniques from feasibility thoughts. If I have this, this cannot be the case because otherwise I will be infeasible. Well, I just told you feasibility is never an issue in this problem. It's just about the dual bound usually. So whenever we now derive propagation techniques, we have to exclude by propagation assignments that cannot be optimal. So this all needs to be and will be optimality-based propagation, kind of. So let's start with a very simple idea. So if you're somewhere in your branch and bound tree, then for every cluster J, we denote with capital Pj the set of points that are already fixed to be part of the Jth cluster in this part of the branch and bound tree. Pj prime is a bigger set. This is the set of all points that still can be assigned to the cluster J. So those points that are not yet assigned to something else. Formally, Pj is a subset of Pj prime. Okay, so now think of a given set of points, capital Q. It should not be the empty set because otherwise we are in troubles by dividing here by 0. So if you have such a set of points, what is always easy in these problems is to get the perfect centroid. It's just the barycenter of it. Sum up all the points that should belong to this cluster and take the mean value. That's the centroid, the optimal centroid. And here you see the value of the loss function. You just sum up all the points that belong to this set, and you have P, the point, minus the centroid given by this barycenter formula here in its norm squared. So this is the loss function for this given set. This is just notation. I will come to the propagation idea in a second. So since we know that if we have a subset of another set of points, we know that the loss function of the smaller set cannot be larger than the loss function of the larger set. So now comes the super easy idea. Whenever you have already some points that are assigned to a cluster J, which is Pj, you can sum the loss function values, d of Pj, for all the clusters, and this gives you a dual bound. That's a lower bound for the subtree given by the node in the branch and bound tree that you right now consider. So this is a local lower bound on your objective function. It's a super easy idea, but we will later see that it helps, okay? Can you do the same with the epigraph reformulation? No, because in the epigraph reformulation, you kind of decouple all these objective function terms. But you can do something, well, similar. So if you, for instance, have a point that is not in Pj prime, so in words, it's a point that cannot be still assigned to cluster J. Because, for instance, it's already assigned to a different cluster. And if you know that the lower bound that you get by the derivations and the reductions from your MINLP solver of the corresponding eta variables strictly positive, you can prune this node. Because if P cannot be in J, you should never count eta Pj in the objective function value. So this cannot be an optimal point if the lower bound is already strictly positive. So you can just prune the entire subtree. On the other hand, if you have the same prerequisite here and the lower bound is still 0, you can fix the entire variable to 0 because you know this eta should never count in the objective function because P will never be assigned to J because it is not in Pj prime. Okay? Okay. What can we do with this barycenter idea for the centroids? So think, for instance, about all the points that still could be assigned to cluster J, but are not yet assigned to this cluster J. Let's give them names, P1 to PS. And let's sort them, if we now only think about the ith component, so that they are in this ascending order. So if you now compute these gamma JR values, what is it? You take the centroid of all the points that are already assigned to J, and then the point 1 to the point R. This R here is this R. And you do this for only Pj, then Pj with P1, then Pj with P1 and P2, and so on and so forth. Because they are ordered in this component, which you can easily do without loss of generality, you get the following lemma, namely that a valid lower bound on your jth centroid in the ith component is given by the minimum of these numbers. The proof is rather easy. If you just draw a picture in order.
Martin, let me just interrupt. I didn't understand when you say you sort the point here. You sort by what? Such that Pi1 is smaller than Pi2?
Yeah,
what?
So Pi is the ith component of the d-dimensional vector P1. Same for P2, same for PS. So fix the component for a minute.
Okay, okay.
Then you can sort because it's not about vectors, but only about numbers, okay? So in this component, you can think now from the left to the right in a 2D picture, and you can compute all these centroids given by the points that you already decided, and then P1, and then P1 and P2, and so on and so forth. And due to this sorting, you get the lemma that a lower bound for the centroid is given by the minimum of these values. You need a few lines to prove it, and if you draw a picture, you see it directly. But unfortunately, that's not the proof. You can do it from the other side and take the maximum, and this gives you an upper bound, okay? Same rational, just think from the right instead of from the left if you draw the picture. Okay. The next idea is even more simple. If you have an optimal clustering, you know that you always have convex clusters. So what do I mean with this formally? If you have these clusters P1 to Pk, if you take for one J the convex hull, and if you intersect it with all points, you get Pj. That's obvious. But you can use it for deriving a very powerful propagation technique. So you compute the convex hull, and whenever you have a point that is in this convex hull, you can do two things. If your point is not in Pj prime, so if your point is in the convex hull of my hand here, which is the cluster, but it cannot be assigned anymore to this cluster in the branch and bound tree, forget about the entire subtree. Prune it. Otherwise, you can fix it to 1. It has to be in this cluster. Otherwise, it cannot be optimal. Sounds like a good idea. It is a good idea. There's one caveat of it. I said compute the convex hull, and we all know that this is hard. So for small dimensions, 2, 3, it's rather easy to do. 4, if you are a patient person. 5, forget it. Okay, so in lower dimensions, this is a very powerful idea. In higher dimensions, we first have to prove P equals NP before this can be turned into an efficient idea. Good. So next, propagator. So you see, it's a bunch of ideas and geometric things that you play with in order to derive rules that tighten your node problems and that allow to prune subtrees, etc. So again, take a partition of your finite set of data points. So if you take now the situation that we had in the last lemma, which is true in an optimal solution, you know that whenever you take for a point P that is not in the cluster J, Q plus the cone that is constructed by minus P minus Q, then everything that is in this cone cannot be assigned to cluster J. So when my co-author wrote this down for the first time, I asked for a picture so that I'm able to understand it. Here's the picture that he drew. The red ones are your Jth cluster. Here's your point Q. Take every red point and shoot rays through Q. What you get is this cone here. All the points in this cone cannot be assigned to cluster J if Q is not assigned to cluster J. Okay, so this is our conic propagator, if you want so. So just, I mean, if you want to remember something, think about the figure and not the formula, at least if your brain works as mine. Okay. One more. And this is a nice example, and then I will talk about something else, where you see that different, well, concepts can, I don't know, I would talk about two more things. First, this one. So, you know, that's the key insight, that a point usually in an optimal solution is assigned to a centroid of minimum distance. That's the idea, right? So you can take for every point P and every cluster J, the minimum and the maximum distance from the point to the set. What is the set? The set is just the bounding box of the centroid variable that you have. If you then have, for instance, a cluster J prime, for which the maximum distance is smaller than the minimum distance for a cluster J, P can never be assigned to J. Fix the variable to 0. Okay, so another geometric idea. So this is about propagation. Let's talk a bit about branching rules. So branching rules, you all know, I guess, but just as a brief recap, if you are in a node of your branch and boundary, you solved your relaxation. If you are not a lucky guy, you do not get a binary feasible solution. This usually is the case. So you have a fractional variable, and you don't only have one, but you have many of them. And then you have usually to pick one in order to construct two new subproblems. Which one to pick is the idea of branching rules. So what do we do here? Well, the intuition should now always be, if you have a fractional variable for your variable xpj, which should be binary, think about it as the probability between 0 and 1 for that your point P is assigned to cluster J. Okay, so if you consider all the fractional variables here, all those that are not binary, since you have this SOS1 constraint, and since they are all non-negative, it's even mathematically valid to think about it as a probability. So the idea now for what we call entropy branching is, well, if we have a point for which all pj variables for all j are the same, there is a lot of uncertainty in this subtree regarding the question to which cluster should you assign point j. This is what you usually in information theory would call a homogeneous information setting. All the fractional variables are 1 over k. So this is bad. Think about the other extreme. The other extreme is what you want to get. You have zero entropy. There is no uncertainty anymore. Okay, then you have decided your binary variable. So think about the classic concept of Shannon entropy. Here it's defined for a point P. So it's just the sum of in probability terms or in information theory terms, probability times the 2 logarithm of probability. You sum it up, take the negative value. This is the entropy. What we want to branch on are those points P that have large entropy, because those belong to the situations where we still have a lot of uncertainty about the decisions that we want to take in our problem. So this is what we do. For a point P, just take the argmax of HP as P star, and then branch on the first variable that you see, that is then X bar P star J, if J is the first thing that you see that is fractional. And by this, you simply try to reduce the uncertainty that you have in the subtree regarding the decisions that you want to take in this MINLP that you solve. Okay, one more branching rule. This is not information theoretic now, or theory now, but another geometric idea. So usually clusters should be compact. They should not be spread out. This is at least what you think of when you think about an optimal solution. So in this, what we call distance branching rule, we do the following. We take the pair of point and cluster that maximizes the distance. So if I said, well, they should be compact, not spread out, this sounds maybe like a stupid idea because we do exactly the difference. But it's not. Why? Well, think about the two situations that can appear. If your optimal cluster in the end indeed is compact, I mean, not in the mathematical sense, but what you think about if you think about a picture, right? Then this means that the zero problem, where you fix the variable after branching X, P star, J star to 0, this will contain an optimal solution. And on the other hand, if you have your cluster here and a far distant point here, and you assign by branching this point in the one subproblem to this cluster, your convexity propagator can be very powerful because you have a lot of points in between. So this distance branching rule together with your convexity propagator can help a lot in order to fix variables later on and to reduce the size of the subtree that you have to solve afterward. So you could always think also about the combination of these techniques in order to derive something that may be, or hopefully is in the end, powerful. Let me skip this. It didn't work so well in practice anyway, and I'm already running out of time. So a few things about heuristics. Well, the first heuristic that you implement is the one everybody uses in practice anyway. This is this k-means clustering heuristic. I explained this very famous idea to you in 10 seconds. Fix a binary assignment, compute a cluster, centroid for every cluster, fix the centroid, compute a new assignment, iterate. That's it. One of the most well-cited algorithms in the last century. And the idea is explained in, I think I didn't even need 10 seconds. Okay? Just implement it. We use it as a primal heuristic at the very beginning. Then there are some rounding heuristics. So you could round, of course, fractional variables, but you have to do it a bit careful. You have to round so that no cluster is empty, because an empty cluster can never be an optimal solution. And then you usually round so that you again consider these fractional variables as probabilities, and you just take the most probable decision. Easy. And then there is still this very bad situation. I show you now this picture for the third time, where you see such a solution. It might be a binary feasible solution, but it's of course bullshit. And then you can try to do a what we call an improvement heuristic. So if you have one cluster, this is the centroid. Excuse me, this is your loss function. We call it also the intravariance of this cluster. It measures kind of the statistical variance in this cluster. So then you can think about pairs of clusters. You can take their joint centroid. Well, this is again the barycenter formula. And you can think about their joint total loss. And now think about the following situation. Namely that you consider triplets of clusters, so that when you have two clusters that you join, and if the total loss is smaller than the loss in one other cluster, you should split this one other cluster, okay, and join the two other ones. Let's go back to the picture and then we can skip the formulas. Of course, you should split this cluster into two and merge these ones into one. And the reason is because these intravariances and the variance of a single cluster are ordered as I did it here in this set definition for psi. So whenever you have a binary assignment, you can use this in order to improve the objective function value and to get a better bound. But this is just what I told you. Okay, so finally, I'm already running out of time. A few numerical results. This is still work in progress. So let's see what we have. We use SCIP. Cplex is the LP solver. Everything is implemented in C++. Well, we have a computer on which we do the stuff. We have a time limit of 1 hour. And for the convex hull, we use the code QHull in order to compute the convex hulls. These are the test sets that we have. So this is this UCI, mainly the UCI machine learning instances that are used in the clustering literature. It's just collected from other papers. You see the papers here. And then there is a paper that presents some syntactic data for testing clustering algorithms by Frenti and Siranoia. I hopefully pronounced this not too badly. So just use SCIP, k equals 2. It's horrible. Think about the original formulation. All runs into the time limit. You never ever get at least a finite gap, except for this one very easy instance here. So if you just take a state-of-the-art MINLP solvers, you cannot solve anything, nothing. It's too hard. If you take the epigraph reformulation, you at least get some dual bounds because you have better inequalities from the outer approximation. But well, as you see, it's not the size of dual bounds that you want to get in the end, right? So now I just go over it. I add now convexity propagator, cone propagator, and the heuristics. Before, after. Just take the original formulation and the gap column. Before, after. So we can at least solve some of the instances to global optimality now, just by using these very easy geometric ideas. The epigraph reformulation, well, before, after, you see numbers are decreasing, but yeah, not that drastically. If you only take the barycenter propagator, you get gaps everywhere here, for instance, but you never solve a problem to global optimality except for the one that is trivial. Combine all propagators, that's really nice. You solve 1, 2, 3, 4, 5, 6, 7, 8 instances, and you get a gap almost everywhere. Remember, we started with infinite gap after 1 hour everywhere. Almost everywhere, except for one instance. Now with the outer approximation, before, after, just take a look at the right column, because the left cannot change, because we can only apply the outer approximation to the epigraph reformulation. So what you see is you get everywhere a dual bound, before, many infinities, after. Okay, so it helps for the dual bound, but it's not yet perfect. if you do all propagation together, if you do all outer approximation, kind of the same figure. Entropy branching, I mean, we are not considering the numbers here. Let me tell you the story. For some instances, it helps, for some not. And this is the case for the other branching rules as well. And don't ask me when to use what. I mean, don't ask me, give me the answer. That would be better because I don't have it yet. Okay. So with this, let me close. So what I did is I showed you a bunch of techniques, all of them, if you consider them separately, not too big, all geometrically motivated usually. And if you include them, you can solve some instances, which was not possible before. You get gaps everywhere, which was clearly not the case before. And we are right now doing some last experiments in order to see up to which size can we really solve instances. So we have some more synthetic data sets that we want to solve where we have a bit more of a trend to show up to what size of instances can we solve these instances, up to which size we can solve the instances. And finally, well, there are these papers from 2021, for instance, here by Huar. This is an ICML paper, or here again, another Journal of Global Optimization paper, where almost everything of these papers, they are published there, by Leo Liberti and a co-author, where the people say, well, we can solve the problem if we sample and solve sub-instances and do this in a smart iteration. But then you need a solver for solving the medium or moderate sized instances to global optimality. So this would be a nice combination. Take these space reduction or data point reduction techniques that are recently published and maybe use our algorithm to solve the problems in every iteration. Okay, and then you can solve maybe even some larger instances. Okay, that's it for today. As said at the beginning, the preprint is not yet there, but it will be soon available behind this QR code. Thank you very much.